So thank you very much for the invitation. So I really appreciate for being here. And actually, I didn't know that record is a natural option. So I agreed, but it seems not many people agreed to record. So anyway, so my talk is partially joint work with my British collaborators and partially with my Asian collaborators. So it's about time change of the discrete model, convergence of the discrete model to limiting process and the time change of that. So let me first discuss about examples that we'd like to kind of generalize. So we are interested in the trap model and scaling limit of the trap model. So here is the first typical example. So we consider continuous time Markov chain on ZD, on Z, and the holding time is just exponential. And we consider conductance, random conductance. And the conductance is, the average of the conductance is being infinity. So it is outside the usual homogenization regime. So the typical case is that the conductance is bounded from below, but it has a heavy tail like this. So in such case, as you can see, if this is a thick bond, then because the transition probability is proportional to the conductance, if the particle comes to near the heavy bond, then it moves back and forth on such heavy bond. So this heavy bond becomes a trap. And because of such trap, the scaling limit is not the usual one. It's, if you scale by the usual square root, then it just converges to the zero process. And if you scale up faster, in this case, if you scale with the order of 1 plus 1 over alpha, where alpha is this alpha stable, then it converges to some process which is not the Brownian motion, but the time change of the Brownian motion. And this was first found by Fontes-Isopi-Newman in the setting of the Bouchaud trap model, which I will explain in the next slide, but was extended to this random conductance setting by L.G. Cherny. So the limiting process is, as I said, Brownian motion on R1, but time changed by this kind of object, which is an integral of local time of the Brownian motion, integrated by the Poisson point process with intensity depends on alpha. So this is a first example we have in mind. And this kind of thin diffusion, because it is a one-dimensional diffusion, you can write down in the Ferrat's sense. So this law behaves, plays a role of the speed measure. So the corresponding heat corresponding heat equation is like this. And as I said, this was first studied in the Bouchaud's trap model, symmetric Bouchaud trap model case. So Bouchaud trap model is, it's again the simple random walk, but it's time changed by the trapping landscape. So on each side you have IID, and this IID has a heavy tail. And this kind of Bouchaud trap model, the scaling limit has been studied by, for one-dimensional case, studied by Fontes-Isopi-Newman. And in the higher dimensional case, it was the scaling limit has been studied by Benarus and L.G. Cherny. So this is one example where we'd like to discuss the generalization. By the way, in the high dimensional case, you also have the scaling limit. If you consider the high dimensional conductance model with a heavy-tailed conductance, Then again, if you scale by the usual scaling, it converges to zero process. But with this scaling, it converges to the some time change of the Brownian motion. But this time change is, clock process does not depend on the original Brownian motion because of the transiency of the process. In the one-dimensional case, because of the recurrency, the clock process does depend on the original limiting Brownian motion. So that's why the its local time appears. So in this case, it's a inverse of stable subordinator, and this stable subordinator is independent of the Brownian motion. And the corresponding heat equation is a fractional called the fractional kinetic equation, and it is described by the fractional time derivative of this operator. So okay, this is the first example, and there's another example that relates to Liouville Brownian motion on R+, but since my time is limited, I'll skip about this example here, and I'll mainly focus on this random conductance with heavy tail. So my aim is to consider such a time-changed process as a scaling limit of strongly recurrent Markov chains in a unified manner on general metric measure spaces. So the aim is, okay, so one-dimensional case, as I explained, it is known, but if you consider more general space where the limiting process has a point positive capacity on each point, in such framework, I like to discuss such convergence in a general setting. And the examples are fractals and also some random media, such as incipient infinite clusters that Manuel explained in the first lecture. And the second part of my talk is to obtain detailed heat kernel estimate for the generalized fin diffusion and generalized fractional kinetic process. So in this first part, we obtain kind of generalization of the fin diffusions on a class of processes. So we'd like to know about the heat kernel of this limiting process. And we also discuss the heat kernel estimate of this. And there is something like, I mean, you can also discuss, consider the generalization of this high-dimensional case. But that work is still ongoing, so I do not discuss about that part. And actually, just last evening, I realized that concerning AIM2, this is a heat kernel for the continuous media, and so it's not a random walk. So I'm afraid the second part is not really the topic of this conference. But since it's, you can also consider a discrete version of the such phenomena, and long-time behavior of the heat kernel should be closer to the limiting process. So it should give some intuition for the random walk on such media as well. Okay, so that's the aim. And so for the first, for the aim of, for the first part, to discuss the aim one, I will discuss the general convergence theorem on strongly recurrent process and general convergence theorem on time-changed process of that. So this part is a general framework. And we then apply this general theory to various concrete models. So let me, to motivate you, let me give two examples where our theorem, general theory can be applied. So one example is a fractal graph. So, so this is a picture of the approximation of the limiting. So you can approximate Sierpinski gasket by the, okay. Oh, thank you. So you can approximate the Sierpinski gasket by a family of graphs, like you can approximate the line by the lattice. And so you can consider the random conductance on such discrete approximated graph. And in fact, in the uniform elliptic regime, we already obtained the homogenization result in the long ago with Kusuoka, more than 20 years ago. So the setting is on the Sierpinski gasket, you put IID conductance with bounded from above and below, and discuss whether it converges to the Brownian motion on fractals or not. By the way, let me remark that in general, the scaling on fractals, the scaling order of the fractal is different from the scaling order of the Euclidean space. But by a suitable scaling, it converges to some non-trivial process, and there is a uniqueness is known in some class of fractals, so you can call it Brownian motion. So the homogenization for the uniform elliptic case is known, has been known. So the question is whether what happens if you consider heavy-tailed. So instead of just considering the uniform elliptic conductance, you put heavy-tailed conductance bounded from below, but tail is alpha stable-like. And then what is the limiting process? So that is one example. And another example is related to IIC. So one interesting example is the Erdős-Renyi random graph at critical window. So Erdős-Renyi random graph is one of the well-known model on the complex network. So it is a percolation on the on this complete graph. So Erdős-Renyi, each pair of bonds are connected with probability p and disconnected with probability 1 minus p. So if it's connected, these two people are friends. And this Erdős-Renyi is known to have a sharp phase transitions. So when the probability of connection is of order C over n, where n is a number of vertices, then at c equal 1, there is a phase transition. So if c is bigger than this 1, then there is only one giant component of size n, and other components are very small order of log order n. And if c is less than 1, then all the connected components are small, so of order log. And at the criticality, when c equals 1, it is known that there are the largest connected component is of order 2 over 3. Actually, there are a sequence of such connected components. This was obtained by Aldous. Actually, it's not necessarily c equals 1. There is a critical window with some smaller order of p. This fact is, holds. And the scaling limit of such giant largest connected component is known by Liouville, Brownian, and Goldschmidt. So they prove that if you consider the largest connected component as a metric space with origin, then the suitable scaled process converges in the Gromov-Hausdorff sense to some random compact set. And this random compact set is characterized completely. It's not tree. There are a random finite number of surpluses, but it's kind of closer to trees. And David Croydon discussed the scaling limit of the simple random walk on such media. So, how the information are transferred. And with this scaling of 1/3, it converges to Brownian. One can define Brownian motion on this M, and it is known that it converges to Brownian motion on M. So we are interested in what happens in the heavy-tailed conductance case. So this is a case where it's just not only two people are friends or not, but also close they are. If there are some people who chat a lot and have a very strong connection. So in such case, what happens as a scaling limit? So that's a question I'd like to propose. So, okay, so these are the examples we can apply our general theory. So let me explain about our general theory. I'm afraid it's a little bit abstract, but let me please keep in mind. I mean, the typical example is this Sierpinski gasket, so please keep in mind the examples. So the framework we consider is a so-called resistance form, and I do not give a definition of the resistance form. It is defined by the so-called Dirichlet form, which is a quadratic energy of the with nice properties. And okay, so there's a we also assume that it is a so-called regular Dirichlet form. So there is a corresponding Hunt process. And the situation is that the corresponding Hunt process has a positive capacity on each point. So it has a very strong recurrency. And in such form, we can define effective resistance in this way. So this is energy. I mean, the discrete case, energy is simply if the conductance is mu xy, the energy is just defined by the square of this. And the Brownian motion on R1, this is just a Dirichlet integral. So these are the typical case, okay, RD. These are the typical examples of the, okay, I mean resistance form case, D equals 1. So these are the typical examples of Dirichlet forms. And okay, in the classical case, if you consider the RD, it is resistance only when D equals 1. So it's not very, I mean, higher dimensional is not included. However, as I said, many fractals and also various random media, especially in the at criticality, like IIC, you can define resistance form on that, and you can analyze the properties of the process. So here are some examples of the resistance form. So Sierpinski gasket, even high-dimensional Sierpinski gasket, and a tree-like object, and a two-dimensional Sierpinski carpet is also a resistance form. And as I said, there is once you define a resistance form, once you can define a resistance form, with a regular Dirichlet form, there is a corresponding Hunt process. So the approach is, instead of discussing the process itself, we use the property of the, the potential theoretical property of the process to deduce various convergence. Okay? So that's the framework of the process we'll consider the resistance form. And we consider a family of resistance forms and discuss the convergence. And in order to discuss the convergence, we need, we'll use Gromov-Hausdorff topology as a convergence, because if you consider, for instance, percolations, then on each level, the space is in a different, it is located in a different space. So in order to discuss convergence, we need to map those spaces into big space, which is done by Gromov-Hausdorff sense. So here's just a definition of the Gromov-Hausdorff, and we should also think about the convergence of the measure. So convergence in the Gromov-Hausdorff topology is convergence on the family of these four things. So if R is a R is a metric, if R is a compact metric space, and together with a measure, so it is a metric measure space with random measure, and we fix one distinguished point. And norm between these two sets of such compact sets are measured by embedding. So we consider we consider a very big space, metric space M, and consider isometric embedding into this space. And so we take a distance between the two images of the spaces. Okay, this should be F prime. And the measure is by the Hausdorff distance. And also the measure, the two measures are measured by the Prohoff distance. You take a pullback of the measure and take a Prohoff distance. And to distinguish point, you should take, okay, I forgot psi, but you embed in the, by this isomorphism and consider the metric, usual metric on M. And the general fact is that this delta C defines a metric on the big space, FC. And this is for the compact case, but one can also consider such Gromov-Hausdorff convergence in the non-compact case. So this is a framework we will consider. So we consider a family of resistance forms. And okay, I forgot to mention that one important fact is that in the resistance form, this effective resistance on 2 points turns out to be a metric. So although this is an analytic object, you can also consider it as a geometric information. So that's an important fact. So we use a resistance metric as a base metric. So our assumption is that there are a family of resistance forms that converge to something in the Gromov-Hausdorff sense. So the typical example is, as I said, line and Sierpinski gasket. So in that case, if you put resistance bar by putting the unit resistor on each bond, then by scaling of 2 to the minus n, and the measure by scaling by 2 to the minus n, you can prove the convergence in the Gromov-Hausdorff sense. And on the Sierpinski gasket case, you can do the same thing with the suitable scaling. In this case, weight is scaled by 3 to the n, so you divide by 3 to the minus n. And the resistance is scaled by 3 over 5 to the power n. So this is the resistance scaling. So these are the examples of the convergence of the resistance forms. And we need, actually, in this joint work with David Croydon and Ben Humbly, we need another rather strong assumption on the growth of volume growth, which is a uniform volume growth, which says that on each n, the ball of radius r is proportional to the VR, where VR is a doubling function. So, okay, if you like, you just consider r to the power d case. So this is a rather strong restriction, but for some reason, in this joint project, we needed such a strong assumption for the volume growth. So here is our main theorem about the general part. Okay, first main theorem about the convergence. So suppose assumption 2.1 folds. So namely, you have a family of resistance, and this with resistance metric, it converges to some resistance form in the Gromov-Hausdorff sense. Then the corresponding process converges in distribution. And furthermore, you can consider the local times, and the local times converges as well. In the resistance form, you always have local times. And the important thing is that you can also prove the convergence of local times. This is very important. So this is a case example I just write down here. So in both cases, these are satisfied. And other examples, like random media, also satisfy the convergence of the resistance. However, in the random media, degenerate random media case, such as IIC or L-linear at criticality, this uniform volume doubling property is not true. This is rather strong condition. However, rather recently, well, it's already more than half a year, but recently, David extended our result and relaxed this assumption. So he could remove this uniform volume doubling condition to a much weaker assumption of the growth of the resistance. Okay, because it's recurrent, it diverges, but the assumption is that it diverges somehow in a uniform way. And such assumption is always true if you consider the compact space. So thanks to this David's extension, one can discuss, one can include various random media. I'll be more precise which part we can do in the random media case, which part we can do with our framework, and which part I need David's generalization. Anyway, so that's a remark about the generalization. And here's one key point, key lemma about the convergence of the local times. We need this kind of uniform continuity, equicontinuity of the Herder, equicontinuity of the local time to prove the convergence of the local time, to convergence of the local time to the limiting process. And this kind of analysis has been done classically in the one-dimensional case, like Blumenthal-Gettul or Gettul-Kesten. But it turns out that one can generalize it in this resistance framework. For instance, one can obtain this kind of Taylor estimate, but you can relate this information of the hitting time to points to the resistance. So if you can control resistance nicely, then one can control this part. And okay, by some computation, you can compute this gamma n. And using the so-called Gaussian's lemma, one can deduce this kind of result. So this is just a small remark that resistance estimate is very important to control the local time. Okay, so this is a general part of the convergence of the resistance forms. So we now have to we now consider the time change. Time change, actually, we only need another measure, convergence of another measure. So in addition to this assumption 2.1, you have family of another measure converging to something. And so the assumption, additional assumption is, new assumption is that in addition to the original measure, this new measure also converges. Then you can consider, okay, time change actually means a change of measure in the setting, in the potential theoretic approach. Meaning if you have a new measure, nu, then by considering the continuous additive function by integrating local time by mu. Actually, in the discrete setting, this is just you just time change by the new time, clock is, you just count the heaviness of the, nu, up to time t. And in terms of local times, it can be expressed in this way. So by the inverse of these continuous additive functions, you have a time change process. So this is how you formulate the time change. I mean, the time change can be formulated using the corresponding measure. So our second theorem, general theorem, is that assume that we have a assumption 2.3, namely the convergence of the resistance form plus convergence of the time changes measure. Then the time changes process converges to the limiting time change process if nu has full support in this path space. And if you don't have full support, then the convergence is a little bit weaker, but in some weaker sense. So these are the main theorem, general main theorem. And now let me explain how to apply these results. And one application is the Liouville Brownian motion on the resistance forms. But as I said, I do not discuss about it. But just one remark is that in such setting, you can also discuss the convergence of the maximum of the Gaussian free field. You can consider, for instance, Gaussian free field on fractals with a zero boundary condition killing at 0, then the supremum of the Gaussian free field on Fn converges to the Gaussian free field on the limiting Brownian motion. So this we can prove as a byproduct of our general theory, plus the fact that assumption 2.1 holds on some framework of fractals. And in fact, with offer, we did some work about the tightness of such tightness of the maximum of Gaussian free field in actually slightly more wider framework. But with this convergence of resistance forms, one can prove even the convergence, not only the tightness. So that is a remark about Liouville Brownian motion. So now let's discuss about the trap model. So, simpler one is Bouchaud trap model, so symmetric Bouchaud trap model. So, for instance, on the Sierpinski gasket, you put this IID on each vertex and do time change depending on this psi. So this time change is heavy-tailed. Then one can define the fin diffusion on this limiting process by using this measure, Poisson point measure given by the Poisson point process that I explained. This measure appeared in the fin diffusion. So, the general result is that the discrete process time changed by this trap converged to the fin diffusion on the process, and the fin diffusion is determined by the inverse of the inverse of the local time with a fin measure nu. So you can define such fin diffusions on the resistance forms, and if you have the convergence of the resistance form, assumption 2.1, then it converges to the fin diffusion. So this is a generalization of this one-dimensional fin diffusion. So here's the explanation why this kind of Poisson point process appears in the limit. So as I said, we time change. In order to observe it, we should observe the convergence of the time change measure. In the discrete level, time change measure is based on this Xn, which is a trap. So Xn bar on point X is weighted according to this trap. Then one can prove that with a suitable scaling of this nu n, it converges to this Poisson point process. And this is easy to prove. I mean, it's a classical. This is, okay, we are considering IID case. So if you take a Laplace transform of this mu n, you can write down precisely what it is, and it converges to this kind of thing. And if you compute this Laplace transform of this Poisson point process, this is a well-known formula. So one can see it converges to Poisson point process. So this kind of fin diffusion you can observe as a time change of the, scaling of the time change process. And so that's the first part. And if you consider random conductance models, things are more complicated because it's not just time change, but also conductance changes. So for instance, if you consider random conductance with heavy tails on each bond, then the transition probability changes. In the symmetric Bouchaud trap model case, transition probability is always fixed, just a simple random walk, just time change. But in this case, the transition probability also changes. So it's highly non-trivial to prove the convergence of the resistance form. And so the framework is you consider heavy-tailed conductance and what happens. And in fact, in some framework of fractals, we can prove the convergence in such, even in this general heavy-tailed conductance. And this is thanks to the previous work about 20 years ago, when when you construct Brownian motion on fractals and try to prove the uniqueness, we need to analyze the renormalization map of this random walk. And this kind of renormalization map has been studied mid or late 90s by, for instance, Christopher Szabo in his PhD thesis, and also by Volker Metz and other people. This is very much involved, but using this renormalization map, one can prove the convergence of the resistance, and from which one can prove the convergence to the fin diffusion. So, for instance, as I promised in the example 3, on the Sierpinski gasket with heavy-tailed conductance, one can prove it converges to fin diffusions. And also, if you consider Erdős-Renyi random graph at criticality, and consider on each level, as I said, not just putting 0 or 1, but with heavy tails, like this. So conductance being bigger than u is heavy tails. Then we can prove that the scaling limit with different scale converges to the time change of the Brownian motion, where the time change is given by the fin measure, inverse of the fin measure. And let me point out that with our framework, we can prove the convergence, but to characterize the limit like this, inverse of the local time, we have to, because of the lack of uniform volume doubling, we cannot apply our theory, the result with David and Humbly. So we need David's generalized version to characterize the limit. But anyway, together with this, one can prove that it converges to fin diffusion. Okay, so that's the first part. And let me now explain the heat kernel estimate on the fin diffusion in the rather general framework. But this is even new for R1 case. So it's it's naturally interesting what happens if you have such trap, how the heat transfers. And we can do both annealed and quenched estimate. Quenched is P almost sure in terms for P almost sure environment of the nu. So it turns out that, okay, so far we obtain mainly on the on-diagonal estimate. We have some result on the off-diagonal, but it's not completely ready, so I only explain on-diagonal. And one can see some oscillation. So the main term is polynomial decay, where df and alpha is alpha stable. This df divided by df plus alpha. But there is an oscillation of log and log. And for limit sup, we know that the oscillation is log. Whereas limit inf, we have an oscillation of order log. And there is a symmetry of the fluctuation. And in fact, this fluctuation, asymmetry of the fluctuation comes from the asymmetry of the fin measure nu. And it is actually derived by the fluctuation of the related subordinator, stable subordinator. Let me explain some more about asymmetry. So in fact, in such case, one can obtain on-diagonal estimate if one knows enough information of the volume in terms of the fin measure. So this is kind of rather general theory on the resistance form. So it is important to analyze volume growth. And it turns out this volume growth is comparable to the R to the power df of the stable subordinator. So here is a definition of stable subordinator. Given alpha stable subordinator, it is well known that if you observe at time t, this turns out to be a Poisson point process that I have been explained. This is the fin measure. So that's why the volume growth, which is described by the fin measure, turns out to be the growth of the alpha stable subordinator. And on the alpha stable subordinator, it is known that short time, long tail and short tail has different behavior. For near zero, we have an exponential decay, whereas a long tail, we have a polynomial decay. So this fact of the asymmetry of the subordinator affects the different asymmetry of the fluctuation of the on-diagonal heat kernel estimates. If you are interested in global estimate, because of the trap, global estimate is kind of trivial. I mean, if you just observe infimum. And supremum, you have more oscillation, log order. But if you take annealed, if you take average over the measure nu, then such oscillation disappears. So if you consider the annealed media, there's no oscillation at all. That is a main part of the heat kernel on the fin diffusions. So for the rest of my time, let me explain the heat kernel for the fractional kinetic case. So this is a case, as I said, so far I explained about the strongly recurrent case. But the fractional kinetic is a scaling limit of the high dimensional trap model, as I explained at the very beginning. So in ZD, when D is bigger than 3, okay, even D equals 2 case with log corrections, it is known that trap models, trap model suitably scaled converge to the fractional kinetic process. And the fractional kinetic process can be, the corresponding kernel can be expressed by the fractional type derivative. And this fractional type derivative can be written by the so-called Caputo derivative, which is explained here. And there are many literatures by PDE using the so-called Mittag-Leffler function, which is kind of using the inverse Fourier transform of this Mittag-Leffler function, one can write down the density. So there are many literatures by PDE concerning this problem. And the question is whether one can obtain such estimate in a much more general framework or not. And actually, here the motivation comes from the question from some industry person about I think 5 years ago, I was asked the following question from someone working in the steel company. So, okay, these slides are from the industry person. So if the very dirty oils goes into the ground, and we want to know how fast such bad things penetrate into the ground. And actually, it is known that such phenomena one can analyze using this fractional type derivative. And there are many literatures on that. And the probabilistic explanation of that is exactly I explained. If you consider trap model, discrete trap model, you know, in the ground is very random. So there are some places where it moves faster, and there are some places which moves slower. And so the naive explanation is because it is a scaling limit of such trap model, such fractional time derivative appears in such media. And actually, they did a quite serious experiment. They have a big box of, I don't know, maybe 10 meters or something, and put sand and put some pollution source, and they study how fast it transfers, it penetrates into the ground. And they knew that such fractional derivative appears, so and there are papers by PD, so they kind of try to match the data. But they realize that the behavior is, okay, it's not exactly written here, but they realize that the behavior is not exactly this fractional time derivative with the usual Laplacian. And they wonder that perhaps this is not a nice framework. You should, perhaps the media itself is more irregular, and for instance, like fractals, and this operator may not be a relevant operator, and should consider more general operator and consider the time change of that. So they asked me whether one can do it in general. And of course, this kind of Fourier transform does not work because there is no translation invariance in general. And that's the motivation we decided to work with Asian. Okay, so this is a part of joint work with Asian collaborators, Chen Sen and Pan-Ki Kim and John Wang. So we consider more general Dirichlet form. And okay, we need information of the heat kernel. So we generalize information of the heat kernel. So the classical heat kernel is a Gaussian. Classical heat kernel is a Gaussian. So let me write in this way. Square. So this is a classical case. And we'd like to generalize it. So instead of the relation of 2 between time and space, we consider alpha. And instead of exponential, we consider this. So the relation between time and space are 1 over alpha, and f is just decreasing. So this is probably some suitable framework. And it turns out, actually, with Sasha Gregorian, we worked on such framework. And it turns out, if you have a heat kernel of this kind, oh, sorry, psi, I write psi, not f. If you have a Dirichlet form, symmetric Dirichlet form that has this kind of heat kernel, it turns out there's a dichotomy. It turns out that f is either comparable to this exponential with alpha or polynomial. And this case is called a sub-Gaussian. It's a fractal is a typical example. And this case is a stable process. Alpha stable process satisfies this kind of property. So alpha equals 2 is a special case. So this can be a reasonable general framework to consider. As I said, there's a dichotomy. So in fact, we only need to consider 2 cases. And how to generalize the operator? Okay, as I said, through PD it's difficult, but from the point of view of probability, it is a time change of the original process, and time change is given by the subordinator. And we also want to generalize the subordinator, not just alpha stable, but with phi. Okay, when phi lambda is lambda to the power alpha, that is alpha stable. But we consider more general operator that satisfies this kind of doubling condition. And okay, so X is a process that enjoys this kind of heat kernel estimates, and S is a subordinator of the general type. And then one can define the generalized Caputo derivative having the probabilistic intuition, one can relatively easy to write down what it should be. Let me compare with the classical case. Classical Caputo case is like this. This is a kind of generalized version of that. And we get a result. Okay, it's kind of messy, but we can, okay, because it's a time change of the original process, it's not very hard to obtain the heat kernel estimate, and one can get the full information of the corresponding fractional time derivative. And okay, so, once again, the key point is that to analyze the asymptotic behavior of the state subordinator, And this is a kind of generalization of the state. Okay, I explained in the stable subordinator case, I explained this in 4.1, but one can get more general version with this phi. And using that, we can get a detailed heat kernel estimate. Okay, I'll stop here. Thank you very much for your attention.
We have time for questions, but I think we will have to use this microphone if we will be able to switch it on. Not sure. Does it work? Yes. Okay. So any question? If you dare.
About the normalization map, it's a random normalization map?
Sorry?
It is random normalization map.
Renormalization map itself is not random. You have a fixed non-linear.
You have random conductance.
Yes, yes. So you should plug in the random information on the fixed. I think you know much better than me about this.
I don't understand how the randomness of the omega enters into the normalization map.
Renormalization map is a nonlinear map that you defined, and then you plug. Yeah, that's not a random one, but you plug in random conductance into there and observe how it behaves. That is what we did. Yeah.
More questions?
Okay, somewhere.
Good, then let's thank Takashi.
Thank you very much.